Hey guys, I'm Nick and welcome to my channel. In today's video we will be creating this two sticky vellum gloss pieces, and we will be detaching one from another. The idea is not mine. Sergey, his username on Instagram is shtdsk. Be sure to check his works. He has some dope Houdini simulations. Of course, I'll link this artwork in the description of this video. As always, before we start, thanks to everyone who is supporting me and purchasing my project files. You can find my website with all of my project files and some cool assets in the link of the description. And for this tutorial, project files are also available. Your support really allows me to dedicate more time to create these tutorials and make them better, so I truly appreciate your support. Now let's get to this setup, and the important note here is the thing that you see on render, and I mean all these details here, these are possible only with a pretty heavy poly count here. For now, I will decrease that poly count just so I can explain you and show you what each node in the Vellum simulation does. But before, we need to prepare some nodes, and I suggest you always using some nulls for controlling your parameters from one node. That's how you don't need to go through all of them and like change something. So here's my controls node, and these are custom parameters. I explain that nearly in every video, but you can click this gear icon, click edit parameter interface, then drag integers, floats, vectors, ramps, anything. So here I drag two integers and two floats, and I've labeled them. So one of them is grid resolution, and it is here. Basically it's columns and rows are multiplied by 15, just so we have this squarish ratio between rows and columns. And it's pasted here. You can just right click and select, nope, here you select right click, copy parameter, and then you go into your, let's say, grid node, and here you can paste relative references, and it will paste. And so also here I have my tiering speed ratio, and it's because we have these boxes and we have our grid top points attached to these boxes, and that's why here we have this little thingy, which is basically initial position, and every frame divided by this tiering ratio, we move our box away from its initial position. Also, what I have here is glue force minimum, glue force max. It's basically controls our glue force attributes. And now, if you don't want to mess with these controls and you just want the base core simulation, I will walk you through all of the geometry and setup and Dopnet works, Vellums, all this stuff. Alright, so what we will need to do, we will need to drop grid, and it's your standard grid. YZ plane orientation, size. It's a little bit off-centered, and I will explain why. And we add a UV unwrap. We need to do UV unwrap for any sort of vellum that is moving, and even if it's not moving, it's a good practice to drop a UV unwrap just before the main node. So then we drop a vellum clause, vellum constraints configure to constraint type cloth. These are the values that work for me with my setup. And for this project, if you will be using different resolution, it will take you some time to get these values right. But for me, the mass was set to 0.0001 and thickness set to 0.005. And damping ratio set to 0.01. Yeah, that's... Oh, and stiffness, bend stiffness is set to the one of the like lowest decimal numbers, which is this 0.000001. Then we basically copy all of that stuff, and after vellum clause we obviously attach one null which is called geo, and the second null which is called constraints. It's attached to the output of the geometry and the output of the constraints. And we basically copied this So let me just merge these two grids so I can show you the positioning of these two grids. So they are very, very close to each other. Then we will need to drop two boxes. Let me merge them together too. So you see, we have these boxes and each grid's top points are intersecting with these boxes. And these boxes basically will be attached to our class, and that's how it will go away from each other, because they will be bind to these boxes. Let me delete the merge nodes. For the boxes, there is this animation. Actually, yeah, let me revert the merge. So they go away from each other too, and as they are bind to grids, grids go away too. Here the thing is, so this is their initial position, minus 0.008. And then I'm subtracting the frame number divided by my tearing ratio, which is 50. If let's say we are on the frame 50, now this value will be minus 1.008, like it is here. Because frame number 50 divided by tearing ratio, which is 50, equals 1. So that's how it works. And increasing or decreasing tearing ratio allows me to control the speed of tearing these grids. I think that's it for now. Let's decrease grid resolution to something like 15 maybe. And now we need to drop a DOP network. An important thing for this setup, especially for these boxes, we need to specify that we are starting at frame 0, and start frame here in the DOP network simulation tab should also be 0. Now let's open up our DOPNet. It will be absolutely empty. So first of all, you will need to add a Vellum solver. You actually don't need gravity, so let's delete that. And in the Vellum solver, we attach the Vellum object. And now we will need to drop two Vellum sources, Vellum source 1, Vellum source 2. It's called Vellum source, this one. In the Vellum source 1, we select our first grid. Geo goes into the subpath and constraints goes to the constraint subpath. And for the Vellum source 2, we do exactly the same thing. And then we will need to attach Vellum constraints. And Vellum constraints constraint type is set to attach to geometry. Group type is set to points, and group is called stream Vellum source 1, which is our first grid, which is on the left side. And we here in the target geometry, we change the target group type to points, and target path should be our corresponding box. In this case, it's the box number 3. This one, box 3. And for the Vellum source 2, we do the same thing. We drop a Vellum constraints, change its constraint type to attach to geometry, group type to points, group stream Vellum source 2, and in the target geometry, target group type set to points, and target path to the corresponding box. In this case, it's box 4. Now for the Vellum source 1, we need to attach the glue. And let me actually show you what it looks if we don't have any glue here. So let's quickly run a simulation. I just want to decrease the Vellum solver substeps. For now, we don't need that high of a number. And let's see. So as you can see here, we don't have any sort of gravity. That's why nothing pulls them down. But basically, that's the correct motion in this scenario. And now let me add the glue. So we drop a Vellum constraints into the Vellum source 1, not in the Vellum source 2 and not to the both of them, just in the Vellum source 1. We change the create constraints to each frame, constraint type to be glue, group type set to points, group stream Vellum source 1, and in the target geometry, target group type set to points, and we target the stream Vellum source 2. So we are gluing our stream Vellum source 1, which is our grid, to another grid, which is Vellum source 2. So here in glue search, my parameters were max search distance set to 0.015, max search points 50, constraints per point 30, stretch damping ratio set to 0.01, and dressed length scale set to 0.9. And in the braking, let's set it for now to be something much higher. For example, let's say something like 2. And we of course should enable this checkbox in breaking and type default stretch stress. So let's simulate and see what we've got. So now you can see that we are definitely glued these two together, but because of the breaking threshold being so high, and also we have just one substep, you can either increase the substep or decrease the glue breaking threshold. But anyways, here with this project I understand that you can't trick the physics that much, and as I said, if you are using your own values, there will be some back and forth until you have decent simulation without these UVs stretching so much. So let's re-simulate that with the breaking threshold set to 0.7. So now you can see that we are not stressing the UVs that much. They are still stretching because maybe we should increase the substeps and constraint iterations. I would say increase the substeps because I ended up using 5 substeps. And just let's see what we've got if we increase that to 4 right now. So I increased the substeps to 4 and already you can see that we have much more linear and not that stretchy simulation. For now, I will leave that at 1, but just remember that you definitely want to use more substeps here. So here we are with just one substep and it's already looking kinda okay, but there's always just little things that make a huge difference between good simulation and great project. I want to make some areas be more sticky and some areas to be less sticky. What we can do here is grab an output of our grid and feed it into attribute noise. And here the node name is attribute noise float, so we want just one-dimensional noise, we don't want any sort of vectors. And attribute names, I created an attribute stickiness and it's set to float. The noise value operations set to set. Range values minimum maximum. Minimum value is minus 0.59 and max value 1. I don't need output raw value, so I uncheck this checkbox. Here in the noise pattern, noise type is set to Berlin and element size is set to 0.085. Fractal type is set to hybrid terrain, max octave set to 0.94, lacunarity set to 1.269, and roughness set to 0.412. Now I want to visualize and just see what type of noise I get. And I drop a color node, set it color type to be ramp from attribute, and attribute is set to stickiness. So now we visualize our noise and we see that all these white spots are more sticky than all the black spots, and this will make our simulation look more natural or realistic. Also here is attribute remap node, and I want to remap the stickiness, which is here in the original name. I want to remap that, and I figured out that I don't want a big difference between the stickiness of these points, so we are using 3.5 and 4, and we are using this for the high-res simulation. For the low-res, that might be way too much. And then we feed this to out params, which is null. Now we need to feed them into the Dopnet. So here we need to drop a Vellum constraint property, and very important thing here, our group should be constraint tag glue, and that's what we should specify here in the glue constraint. Here you can see the tag, and I set this tag to be glue, so now I can reference it here in the constraint tag equals glue. Now to be able to access our params null here in the inputs, we should go and specify that our input 3 is SOP, and we should target our out params. Now in the properties we should enable our break threshold, and here we should write some code. So we write float stickiness equals point, and this point function grabs an attribute from the point, and we should grab the stickiness attribute from the input number 2. And if you ask me why it's input number 3 here, because for our convenience these inputs are numbered by 1, 2, 3 and 4, but in code the count starts from 0, so it's 0, 1, 2, not 1, 2, 3. And the point from which we want to grab the stickiness attribute is set to ptnum, because this wax goes through all the points. And now we set our break threshold to be equal to the value of the attribute called stickiness of our points. So let's see how it is in the simulation. Now that's what I was saying, so it's definitely too much for this low res mesh. So let me decrease this by, let's say, 3. So here we decrease the noise, and if you look closely, we have some areas that detach quicker than other ones. Especially it's visible here in this area, and if I go back, you can see that in this area these points here are black, and that means that they receive much less glue than all these white ones here, talking about these. Now here in the Dopnet I merged these two Vellum sources, added a little bit of pop drag. Here in the Vellum solver, yeah, definitely up the substeps to something like 5 and 500. In the velocity damping 0.01, dynamic scale set to 0.5 and static threshold set to 1. In the advanced tab, everything's as usual. Now our simulation is done, and we should drop a dop import node and select the Dopnet. Here we can select this Dopnet, and import style is set to fetch geometry from Dop network. So here I've already cached all of this simulation and in high res, and we are rendering this. Nope, not here in the Houdini. We will be bringing this to Cinema 4D. I'll explain to you why we need these two groups. So we want to convert two of our groups, which are point groups, Stream Vellum Source 1 and Stream Vellum Source 2, to be primitive groups. So we can access and set up different materials to both of these two pieces of cloth. So we drop a group promote and set the convert from points to primitives. Group name Stream Vellum Source 1, and I named it to be close 1. Then we drop another group promote and also convert it from points to primitives, and group name Stream Vellum Source 2, new name close 2. Now what I want to do is fix the normals and maybe subdivide it once more. So we drop a Vellum post process node, and here I set the subdivision to be Catmull-Clark subdivision depth 1, and I've extruded by the thickness by 0.8. So this is how it looks. And then I just exported the alembic. Let's open up Cinema 4D and I will show you how I set up the scene. So you just drag and drop your alembic. So we have our UV map and we have some polygon selections. So what we need to do is to find our cloth 2 and cloth 1 obviously, and that's how you can assign materials to the cloth. I got this leather here, and I also have the frosted glass. 3-point light system, which looks like this. One top light, side light, and I assume the fill light. So this one is somewhere here, and then this one is our just tiny light that makes this edge glow, and then we have our kind of like a fill light. For the Octane sky there's nothing, just the backplate, but I will already render that with a black background. Oh, and also you can see that half res, and I'm rendering this 1080 by 1920, and half res takes 2 minutes, so it's fair to say that one frame would be 5 minutes on my machine. But we have our friends Fox Farm, and they have done it in less than an hour, I think. So it cost me $12 to render out 300 frames, and I was rendering 10 frames per node. And here you can see the resolution, all the stuff. All the frames are top quality, and I'm super glad that I found them. And there's my affiliate link in the description. If you want your renders done fast, cheap, and with awesome quality, be sure to check that link in the description. You can sign up. It's very easy. They have their client here. You just drag and drop your scene and that's it. Check these guys out. So for the camera, focal length set to 80. Yeah, nothing too crazy here. So I think that's it for today, guys. Thanks a lot for watching, and if you enjoy my tutorials, please be sure to like this video, subscribe to my channel, click the notification bell, because I have a lot of tutorials to share with you. And of course, you can grab the project file Cinema 4D file, Houdini file with all the assets on my Gumroad. Link is in the description. I'll be back very soon. Bye!